To our next presentation, which is from Mr. Ambika Shankar Shukla. He's a PhD student at IIT Bombay. He's working with Professor Ashwin Tulapurkar, and he'll talk about large VCMA effect at metalloporphyrin decorated graphene ferromagnet interface. So please share your screen.
Sure, Naveen. So, can you hear me?
Yes,
Uh, can you see my screen?
and yes, I can see you. You can go to full screen and you can begin. Thanks so much.
Sure. Okay. So, I'll start then. Uh, Very good evening to all of you. My name is Ambika Shankar Shukla, and my presentation for today is on a large VCMA effect on a graphene and ferromagnetic interface.
ఉందండి
Hello.
ఇట్లండి ఇప్పుడు ప్రజెంటేషన్ ఏంటి
I can hear some
I,
disturbances.
I think someone is.
Okay, now it's fine. So, I'll
It's
start
fine.
then. Yeah,
Thank you.
sure. Okay, so the content for my today's presentation is the motivation behind starting this project. Then I'll go for the device fabrication and then some experimental results, and then I'll conclude finally. So the idea behind starting this project is lies some concept like enhancing the spin orbit coupling at the graphene and ferromagnetic interface. And the molecule or the organic route that we have chosen for this is lies on a molecule called porphyrin. The idea behind choosing this porphyrin was that this ring that you see can be doped with a heavy metal in between, in center of it. So basically, we have chosen platinum as a heavy metal. You can also have a tantalum or tungsten in between, I mean, in a center of this porphyrin ring, and then you can functionalize your pristine graphene using a spin coating method and some heat treatment for actively porphyrin doping to activate this porphyrin doping on top of your pristine graphene. So this is how we have started. The very first experiment that we did is basically, so we have purchased a graphene from a company called a Graphenia from Germany, and they used to sell this graphene, monolayer graphene, onto a copper foil. So we have taken a wet etching route for transferring this graphene onto our silicon dioxide substrate. And the very first experiment that we did is Raman experiment. So we have transferred this graphene onto our silicon dioxide substrate, and we did Raman on a full spectra. And then we find that if we actually see the ID by IG ratio of these two modes, so we find that this defects is not prominent. So we are not introduced any kind of defect when transferring. And then also we have fitted this 2D peak with a Lorentzian, and we find that it fits for a single Lorentzian. So basically it indicates that it's a monolayer. So this is the first experiment that we did. After that, we find that while loading this graphene onto a sputter system, it creates a lot of damage to graphene. And sometimes we also find that it also gets etched from some portion. So to optimize this, we have actually optimized the angle of deposition in our sputter system, and this is what we called it as a grazing angle deposition. So what we found is, again, going for the Raman to and fro, we found that this ID by IG ratio could be decreased to 10 folds if we actually go for angle between 45 degree to 90 degree. So this is how we have optimized the deposition condition for ferromagnetic films on top of graphene. And the experiments that we did after optimization of a sputter, we made something called backgated graphene field effect devices. And idea behind doing this kind of GFET devices was to see how electrically active these dopants are on your graphene. So what we did is then we just simply made source drain contact and then a channel called a graphene channel, and we were interested in doping this graphene channel with our porphyrin with different polarities, and we found that if we actually dope this graphene channel, then this direct point could be shifted. So basically your charge neutral point or your direct point, you can see that it is shifting with respect to voltage basically. So this is what we have observed, and we have also find that we are actually using a different polarity of this porphyrin then this shift is almost linear. So these are electrically active dopant onto this graphene, and this we have confirmed with this simple DC characterization of GFET. Now, coming to the device fabrication, it's very simple fabrication after optimization. What we did with the Sparta system, because lithographically we did not find any kind of challenge, as this graphene is now being protected from permalloy and capping layer of a silicon dioxide. So we have used simply optical lithography for patterning this device, the strips, that is 20 micron cross 50 micron, and simply a gold contact on top of it. So it's a simple fabrication for this. And only thing is that we have actually used some thick chrome gold, close to some 200, 250 nanometer for this RF measurement. So now we started measurement. So we have set up the experiments in this form. So we have actually used the vector network analyzer as a source, and nanovoltmeter for detecting the signal with the bias. And along with this STFMR, what we did is then we have also applied a backgate voltage, as I have shown for the GFET device measurement. So we have applied this backgate voltage, and we have measured this STFMR spectra with respect to VDC. So the STFMR spectra that you see on right of yours is basically we have obtained with applying no gate voltage. So it's a simple STFMR spectra. Now, if you see, the analysis of the spectra is pretty very simple. So what we did is that we have actually used this function, which is a symmetric Lorentzian and asymmetric Lorentzian, the sum of symmetric and asymmetric Lorentzian, and we fit it on top of our experimental result. And the values that we have obtained from this, or we have noted from here, is the resonance field and the del H. So delta H, now in this, what we have found is that if we apply a gate voltage and we plot this delta H as for different gate voltages, we will see that this actually modulates. So you can find that the slope actually changes with respect to voltage. And also we have obtained the alpha from here, and we found that this is also following a linear relationship with respect to voltage, and it also gets modulated. Similarly, your resonance field or your resonance frequency also get changes with respect to gate voltage. So basically, these are our main findings, and we are doing some more controlled experiments for validating these experiments and in further run. But this is our condition. I mean, this is our recent findings about this graphene ferromagnetic interface, and so we have. So I'll conclude with this quickly, that we actually see this kind of modulation only for porphyrin doped graphene, and no modulation of parameters of any so has been obtained for the pristine graphene. So there is no modulation for pristine graphene. Whereas if you modulate, if you dope this your pristine graphene with a porphyrin, your platinum doped porphyrin, you will see these kind of modulation. So thank you very much for your time. It's very quick, and if you have any questions, I'll be more happy to answer them. So.
Yeah, thanks a lot for maintaining the time perfectly. Audience, it's open to you. If there are any questions, please go ahead. Yes, Mudlisa, please ask your question.
Yeah, so I was wondering why all the parameters are being affected, because the resonance field may be because of the, as you said, voltage control anisotropy, but why is the line width changing?
So, Professor Pranav, currently I can say that this porphyrin, what we are using as a electron doping center for graphene and ferromagnet, it creates a lot of electronic states in graphene, and that is actually been responsible for this. But to answer this, we are actually doing more experiments with our PPMS, and still we are confirming this line width modulation along with alpha modulation. So we are still onto working on this actually.
Okay.
Yes, sir.
But this line width you have extracted is very narrow frequency range, only 2 gigahertz. Is it because the signal goes down at high frequency, or what is the reason?
So no, up to 6 gigahertz we have obtained. So you can see in this we have went through some 6 to 6.5 gigahertz.
Okay.
So STFMR spectra, if you look at, then here I'm showing till 6 gigahertz. So we can easily see this signal up to 6 gigahertz, but then it goes down actually if you go for 7 to 8 gigahertz.
Yes, yes.
All right. Are there any more questions? If not, let me thank you again for the interesting talk, and we move ahead to the next speaker. The next speaker is Mr.